Welcome to WikiPodcast. Okay, let's unpack this. Today, we're diving deep into something, well, absolutely fundamental, how things move, how they interact. We're talking about energy and work, the bedrock concepts of classical physics.
Exactly. You could say it's about the mechanics of movement itself. We're not just, listing definitions here. We want to explore how these ideas explain everyday things. Why does a drop ball speed up? How do machines actually work? So we'll take the source material we have and really pull out the crucial insights, make these potentially tricky ideas clear, maybe even a bit surprising.
All right, sounds good. So let's start right there. When physicists talk about work, it's definitely not the 9 to 5 kind. What's the physics definition?
Right. In physics, work has a very precise meaning. It's the energy transferred to an object, or maybe from an object, when you apply a force, and crucially, that force acts along a displacement.
Okay, so the simplest picture then is like force times distance. If I push a box, it moves. I did work. But you said along the displacement. That's important.
That's the absolute key. It's not just force and distance. The force, or at least a part of it, has to point in the same direction the object is actually moving. If you push straight ahead and the box moves straight ahead, great. That's positive work, maximum effect. But say you're pushing sideways, but the box only slides forward. That sideways push is doing zero work regarding the forward motion. Mathematically, we often say work equals force times displacement times the cosine of the angle between them. W equals S cos C.
Ah, the cosine part handles the directionality.
Exactly. Same direction, angle is 0, cosine is 1. It's just F times S.
Okay, so what if the force fights the motion? Like friction slowing things down.
Good example. Friction pushes back, motion's forward, the angle's 180 degrees, and the cosine of 180 is -1. So the work done by friction is negative in that case. It's taking energy out of the motion.
Or like lifting something. Gravity pulls down, but the object moves up.
Perfect. Gravity is doing negative work on the object as you lift it. But if then drop it.
Then gravity pulls down and it moves down. So positive work by gravity.
You got it. Positive work done by gravity in that case.
So it seems like positive work kind of adds energy, negative work removes it. Is that fair?
That's a good way to think about it. Work is that process of energy transfer. And importantly, work itself is a scalar.
Scalar, meaning it just has an amount, a magnitude, but no direction.
Precisely. It's just a quantity of energy transferred. Doesn't point anywhere.
And the units are joules, Jay, same as energy. That really drives home the connection, doesn't it?
It really does. 1 joule is defined as the work done when 1 newton of force moves something 1 meter. You might see newtometer sometimes, which is dimensionally correct, but we usually stick to joules for work and energy to avoid confusion with torque. Torque is a vector, a twisting force.
Right, okay. It feels so neat and tidy now, but these ideas didn't just pop up fully formed, did they? How did we get here?
Oh, absolutely not. It was a long evolution. The ancient Greeks were brilliant with statics forces in balance, things not moving, but dynamics, the study of motion and energy transfer, that really took off during the Renaissance.
Was that linked to studying machines, levers, pulleys, that sort of thing?
Exactly that. People like Galilei, back around 1600, were looking closely at simple machines. He realized something crucial. These devices don't magically create energy, or oomph, as you might say. They just transform it. They let you trade force for distance, essentially.
So even before the formal term work, people were seeing this trade-off. That force times distance was somehow equivalent.
Absolutely. It's fascinating to see the concept bubble up before the name. You mentioned the source material points this out, like Descartes in 1637 saying lifting 100 pounds 1 foot twice is the same effort as lifting 200 pounds 1 foot once.
Or Leibniz, a bit later, saying raising 1 pound 4 yards requires the same force, he meant work, as raising 4 pounds 1 yard.
Yeah, they were grasping that product, force times distance, represented something conserved or equivalent.
But the actual word work for this specific physics concept, that came later.
Much later, relatively speaking. It was formally introduced in the 1820s. Scientists like Gaspard Gustave Coriolis and Jean-Victor Poncelet, they were analyzing engines, steam engines, water wheels, early industrial machines. They needed a precise term to quantify the useful energy output produced by forces causing motion. And work, or travail in French, became the standard.
Okay, so work is energy transfer. That naturally leads us to the core relationship, the work-energy principle.
Yes, the link is fundamental. Same unit, same essence. The work-energy principle makes it explicit.
So lay it out for us. What does it state?
In its simplest form for a particle, it says, the total work done by the net force, that's all the forces added together acting on an object, equals the change in that object's kinetic energy. So 1 net.
And kinetic energy is the energy of motion, right? Depends on mass and speed squared.
That's the one. So the principle tells us directly, if the network is positive, the object speeds up. Its kinetic energy increases.
And if the network is negative.
It slows down. Kinetic energy decreases. It's a very powerful tool.
Why powerful? Does it save calculation steps?
Sometimes, yes. Instead of using Newton's second law, F(na), to find acceleration, then kinematics to find the final speed, you can just calculate the total work done by all forces. That total work directly gives you the change in kinetic energy, and from that, the change in speed. But we need to be careful about different types of forces here.
You mean like conservative forces? You mentioned those earlier.
Right. Forces like gravity near the Earth or the force from an ideal spring, they're called conservative because the work they do getting an object from point A to point B, well, it doesn't matter how it gets there.
The path doesn't matter.
Exactly. Straight line, wiggly path, loop to loop. If the start and end points are the same, a conservative force does the same amount of work. And because of this property, we can define a potential energy, EP or U, associated with them. The work done by a conservative force equals the negative of the change in its potential energy. It just reses now.
Okay, that makes sense. So as gravity does positive work when something falls, its potential energy goes down. The energy changes form.
Precisely. It's converted from potential to kinetic. The work is the mechanism of that conversion.
This leads to something that feels a bit weird, though. The idea that forces can exist, push or pull, but actually do no work at all. How does that work? Or rather, not work?
Oh, right. This often happens with what we call constraint forces. Think of the force from a tabletop holding up a book, or the tension in a string swinging a ball around. These forces constrain the motion. They limit where the object can go.
Okay, so what's the key property that makes them do no work?
For ideal frictionless constraints, the constraint force is always acting perpendicular to the direction the object is moving at any given instant.
Back to the cosine. WS cosine. If the angle between force and displacement is 90 degrees,
then cos 90 is 0. So the work done is 0, no matter how strong the force is.
So the force is crucial for changing the direction maybe, but not the speed.
Exactly. It redirects the motion without transferring energy that changes the kinetic energy. The source material gives some great examples. Like the normal force from a frictionless table pushing up on a sliding block. It does no work. Or the tension in the ropes of an ideal pulley system.
What about the ball on a string? Swinging in a horizontal circle at constant speed, the string pulls inwards.
Yep, the centripetal force from the string pulls towards the center. The ball's velocity is tangent to the circle, always perpendicular to that inward pull. So the tension changes the direction of the velocity, keeping it moving in a circle, but does 0 work. And that's why the speed stays constant.
Wow, okay. The force changes velocity, because direction changes, but does no work. So kinetic energy and speed is constant. That's subtle.
It is. Another classic example is the magnetic force on a moving charged particle. Remember, F equals QV(x)b.
Vaguely. The cross product means the force is perpendicular to both velocity v and magnetic field b.
Right. And because the magnetic force is always perpendicular to the velocity, it does no work. It can bend the path of a charged particle, make it curve, but it can never change its speed or its kinetic energy.
Fascinating. Okay, so we've got the basic W, F's S cos, but what if the force changes or the path is curvy? How do physicists handle that?
That's where calculus comes in. It's essentially about summing up lots and lots of tiny contributions. The most general way is using a line integral. We imagine breaking the path into tiny little steps and calculated the tiny bit of work, FDS, the dot product, for each step, then adding them all up, FDS.
The integral sums the work along the path. And you said earlier this is usually path dependent.
Generally, yes. For forces like friction, the longer the path you take, the more negative work friction does. The route matters.
But not for conservative forces. That's what makes them special. Their work integral isn't path dependent.
Exactly. Only the start and end points matter for them. That's why a potential energy works for them. And if the force itself varies, like a spring where the force F equals Nash kx, depends on how much you stretch it, x, you have to use an integral to find the work done in stretching it, F dx.
You also mentioned power earlier. Relating work to power.
Yes, another angle. Instantaneous power is the rate at which work is done. It's P equals FTT valia, the dot product of force in instantaneous velocity. So if you know the power being applied over time, you can integrate the power with respect to time to find the total work done. Work is the integral of P dt.
And for rotation, like a motor turning something.
Similar idea, but with rotational quantities. Work is done by a torque, T, causing an angular displacement. The instantaneous power is torque dotted with angular velocity. And the total work is the integral of that power over time, or for a constant torque aligned with angular displacement, it's just WT day.
Okay, let's tie this back to the work energy principle, WUSTEC. How does this play out in some real-world examples from the material?
Okay, so remember, it's the total work done by all forces that equals the change in kinetic energy. But here's a neat thing. If we have ideal constraints, like frictionless surfaces, inextensible strings, those constraint forces do zero work, so they don't contribute to one net. This means we often only need to calculate the work done by the applied forces, or forces like gravity and springs, to find the change in kinetic energy.
Ah, that simplifies things. Okay, what about those examples, like the skidding car?
Right, a car slams on its brakes and skids. The main force doing work is kinetic friction from the road. It acts opposite the motion.
So it does negative work.
Exactly. And that negative work reduces the car's kinetic energy, eventually bringing it to zero. We play till 0 12 mil of initial loss elevator. So the work done by friction, which depends on the friction force and the skid distance, is directly related to the car's initial kinetic energy, and therefore its initial speed.
Makes sense. What about the gravity racing example, coasting down a hill?
That's a fantastic illustration, especially about conservative forces. As the car rolls downhill, gravity is pulling it downwards, and it's moving downwards, at least vertically. So gravity does positive work, increasing the car's kinetic energy, making it go faster. Of course, air resistance and friction would do negative work, but let's ignore them for a moment.
And the key insight from the source material was
That the work done by gravity only depends on the vertical height difference between the start and end points, UC or days. It doesn't matter if the hill is straight and steep or long and winding.
same vertical drop, same work done by gravity.
Yep. And if gravity is the only significant force doing work, then the change in kinetic energy, and thus the final speed starting from rest, will be the same regardless of the path shape. It only depends on how far down it dropped vertically.
Wow, that really drives home the power of potential energy. The path is irrelevant for gravity's work.
It really clarifies things. The material even puts numbers on it, suggesting that to reach about 60 miles per hour, coasting down to 6% grade, you need to travel about 2,000 feet along the slope, which corresponds to a specific vertical drop. It's just gravity converting that potential energy, ANGA edge, into kinetic energy, 12 milliVOA, via work.
It's amazing how these seemingly simple concepts, force, displacement, energy buildup, to explain so much about motion.
Absolutely. Work is energy transfer, quantified by force and displacement, the direct link to changes in motion via the work energy principle, and those interesting cases of forces that guide motion without transferring energy. It's all part of the elegance of classical mechanics.
So we've covered the definition of work, how it evolved historically, the crucial work energy principle, those non-working forces, and how we calculate and apply these ideas from skidding cars to coasting downhill.
It really is powerful. Thinking about pushes, pulls, lifting, falling, not just as actions, but as fundamental processes of energy transfer, quantified by work. It connects force and motion in such a deep way.
Thanks for listening. Write us your opinion in the comments on how does understanding work and energy change the way you see movement around you. Subscribe to the channel to help more listeners reach our episodes. Thank you and have an amazing day.